He's visiting us for a couple of months, so his fields of research actually cover quite a broad range, so many of you might want to chat to him at some point during his visit here. He's going to be here until the beginning of August, I think. So he did his PhD at Yale, and then went to Italy in Trieste at CISA for a couple of years, and then postdoc in Amsterdam for 2 years, Amsterdam University, and then spent 7 years in Southampton University as a reader. And his main areas of research include compact object accretion, including populations, and also fast timing analysis, including analysis techniques of rapid variability in accreting objects. One of his topics is globular clusters, and in fact he discovered the first confirmed black hole in a globular cluster. So let's welcome Tom and take it away.
Okay, so thank you for having me over here. Yeah, I turned it on before Dave started, yeah. Before I really get started, I want to at least flash the names of a lot of the collaborators in this work. I'm going to talk about several different results and try to kind of put things together. That's why there's so many collaborators on here. But for almost all of the projects that I'm going to be talking about, Arnav Kundu and Steve Zepp were quite valuable collaborators. Okay. And so first, a little self-indulgence. This is my National Independence Day today, so I just wanted to put a little slide up there. The first time I ever gave a talk at an institute other than my own was on Thanksgiving back in Amsterdam in November of 2002. So it's kind of a tradition for me. Okay, so now on to the science. So let me start off by giving you a little bit of an overview of what the talk's going to be about. So I'm going to start off by talking about the motivations for looking for black holes and neutron stars and globular clusters. Give an overview of the dynamics of star clusters. Talk about how we go about finding black holes. I'll talk about X-ray sources in extragalactic star clusters, the first detections of globular cluster black holes, and along the way, I'm going to talk about some fundamental physics that we can do when we find black holes in globular clusters, and some useful constraints on galaxy evolution that were sort of byproducts of this work. And so a lot of that stuff is actually going to be stuff that was done by Mark Peacock, who was a PhD student of mine, who's now a postdoc at Michigan State. Okay, so there's a few different motivations for understanding binary stars and clusters. And so I'll start off a little bit more generally than talking about black holes and talk about binaries in general. One is that if we look at this cluster, this is an image, I think, of 47 Tucanae, we can see that it has quite a pronounced core to it. And if you look at what theoretical calculations say should happen to globular star clusters, they should all collapse completely and not have cores. Right? So the explanation that's been developed over the years is that what's happening is that the binary stars in the cluster are acting as a heat source that is preventing the core from collapsing all the way. There's something called Heggie's law that Douglas Heggie up at the University of Edinburgh came up with in 1975. He's actually quite a modest man, so he wasn't the one who named it Heggie's law. Other people did that. But what he said is that hard binaries get harder and soft binaries get softer. And the basic idea is that if you have a binary system and a third star flies by near it, if the binary is a tight binary, the velocities of the two stars in the binary are going to be faster than the typical velocities of stars that scatter off of them. And so what will happen is they'll transfer some kinetic energy to the third star, and then as they transfer kinetic energy, they lose kinetic energy and the binary shrinks. Right? So if you have close binaries, they inject energy into the star cluster. If you have wide binaries, they absorb energy, but then they fairly quickly become destroyed. So if we look at globular clusters, the binary fraction in clusters is a lot lower than in the field star populations, but the binaries that do exist tend to be tighter and much more dynamically important. Another motivation that we have in the lower right panel here is we have a color magnitude diagram for a globular cluster. What we can see is we have a nice main sequence, we have our subgiant branch, we have our giants, we have our horizontal branch stars, but above the turnoff we have a bunch of stars here. Right? And these stars shouldn't be there unless there's quite a large disparity in the ages of stars in the cluster. So in the past decade or so, there's been some evidence that's been developed that globular clusters do have multiple populations to them, but it's thought that the difference in the ages of the two populations is a few hundred megayears, not the several gigayears that you would need to produce these stars on the extension of the main sequence. So what's thought instead is that these stars, which are called blue straggler stars because they're bluer than the main sequence turnoff and they seem to be evolving too slowly, are formed from some kind of merger between two other stars, either in a direct collision between two stars or by a close binary pair coalescing. Right? And what this means is that for most of the lifetimes, these two stars are sitting there at, say, half a solar mass and and burning their nuclear fuel fairly slowly. And then when they combine into one star of one solar mass, they have a lot more fuel left than a typical one solar mass star should. Right? Now, another motivation is gravitational wave sources. So there are a few reasons why we might expect gravitational wave sources to be, from globular clusters, to be important in ways that gravitational wave sources from the field can't be. First of all, if we look at the metallicities of globular clusters, they are often, but not always, significantly lower than metallicities of field star populations. So like in our own Milky Way, we have globular clusters which are mostly at a metallicity of around 1/30th of solar metallicity, but they do span a range from about 1% all the way up to solar metallicity. And at low metallicity, stellar winds are weaker than at high metallicity. So you expect that the remnants of those massive stars that form at low metallicity may be a bit heavier than the remnants of massive stars at high metallicity. And then if you have two black holes that merge out of that process, you might be able, in the galaxy, we see black holes mostly around 8 solar masses. In globular clusters, they might go all the way up to 30 solar masses or so. And if you have two 30 solar mass black holes merging with one another, the volume out to which you can see those is much larger than the volume out to which you can see 8 solar mass black holes merging. So we'll have to wait and see what happens with advanced LIGO, but it may turn out that the double black hole merger rate will be dominated by globular cluster systems. Another reason why the masses of the black holes might be higher in globular clusters than in field star populations is that in field star populations, the black holes that we've measured so far are all in close X-ray binary systems. And in these close binary systems, the stellar evolution goes through a phase of what we call common envelope evolution, where two stars are sitting in one envelope, and then eventually a lot of that envelope is ejected. And that also leads to reduced black hole masses. So it may be that the black hole masses that are being measured nowadays are not really representative of what goes on in normal stellar evolution. In globular clusters, we can form isolated black holes and then have them end up in close binaries later on through dynamical interactions. So that may be another way that we can get higher black hole masses for our mergers. A third issue is that some of the binary evolution theorists think that you can't actually get a double black hole system to form through binary evolution without some extra dynamical process coming in, because as the second star evolves off the main sequence and becomes a supergiant, it'll essentially form a giant common envelope with the black hole that's already there and eject so much mass that it can't form a black hole anymore. So this is a more speculative issue than the other two, but it may be that we'll only see double black holes in globular clusters. So a history of the topic of black holes in globular clusters. So Weiler had a couple of papers in 1965 and 1970 where he suggested that globular clusters were quasar remnants. So at the time, right nowadays this sounds like a ridiculous idea. At the time it wasn't so ridiculous. So at the time all they knew about quasars were that they are at much higher redshift than anything else we saw in the universe. And so suggesting that they had some connection with the oldest stellar populations that we knew of at the time wasn't so crazy. So later in the mid-70s, there was a rash of papers suggesting that globular clusters had central black holes of around 1,000 solar masses. So this was around the time when people started to have the first inklings of the idea that supermassive black holes sat at the centers of galaxies. But also what happened was in the mid-70s, with the Uhuru satellite, they started detecting X-ray sources from globular clusters in the Milky Way. And they detected them at a much higher rate than what you would have expected just from the number of stars there if you scaled to the field star binary populations. So it was surprising that they detected anything. At the same time, Newell, DaCosta, and Norris in 1976 took some measurements of the velocity dispersions and the surface brightness profiles of stars in the cluster M15. And what they found from looking at this was that the mass-to-light ratio of M15 shot up in the center of the cluster. Illingworth and King pointed out the next year, I think probably they had the idea in their mind as soon as this paper came out, and they just had to write it down. They pointed out that there's a process called mass segregation that I'll discuss a little bit more in a few minutes. And due to mass segregation, you expect all the white dwarfs and neutron stars in a globular cluster to end up at the center of the cluster. Of course, white dwarfs and neutron stars have extremely high mass-to-light ratios in the optical. So seeing a high mass-to-light ratio in a globular cluster isn't alone enough evidence to prove that you have a black hole there, in the same way that it might be in a much larger stellar population. Essentially, there was this big debate in the 70s, and then what happened was very shortly after the discovery of the initial X-ray sources, they also discovered some bursts from these X-ray sources, and these bursts, after a period of time, a consensus developed that what the bursts were that essentially the neutron star version of classical novae, that material was piling up on the surface of a neutron star, and then undergoing runaway nuclear fusion and producing a very sharp burst of X-ray emission. And whereas in classical novae, this process takes about a week, on the surface of a neutron star, it takes 10 to 100 seconds or so. And so once the consensus developed that these bursts were from the surface of a neutron star, it also turned out that all of the globular cluster X-ray sources in the Milky Way showed these bursts, and therefore there was no reason to think that there were any black holes in the globular clusters. All right, so now I want to talk about a few key timescales for evolution of star clusters. So one of them is the crossing time, and this is a very simple number. This is just the amount of time it takes for a star to cross the star cluster. And that's basically just the radius divided by the velocity. And so for a typical globular cluster, that'll be about 10 to the 6 years. The next one is the relaxation timescale. So I should mention that a lot of the early work in understanding the dynamics of star clusters involved treating star clusters as though they were a gas. And this is actually a very reasonable way to think about things. A lot of the basic thermodynamics of gases applies to star clusters. You just have molecules that are about 10 to the 57 times as massive as the molecules that you normally deal with. The stars in a cluster should end up relaxing to a roughly Maxwellian distribution of velocities. And so the relaxation time scale is about 0.1 n over log n times the crossing time. And so for a typical globular cluster, that'll be about 10 to the 9 years. Okay, now, there's one catch here, which is that this is a self-gravitating Maxwellian distribution. And so in this self-gravitating Maxwellian distribution, the objects that have more than twice the mean velocity are also going to be above the escape velocity. And in a Maxwellian, that turns out to be 1 out of every 136 particles. So what will happen is those objects will escape, and then you have this empty part of the Maxwellian distribution that you need to refill in, and that'll take another relaxation time scale. So the cluster should evaporate itself on a time scale of around 136 times the relaxation time. So I just put that 136 there just to give you the intuition of where it comes from, not because this is as exact as that makes it sound. And so this is all assuming that everything is single stars of equal mass. If you throw in close binaries, you can actually accelerate these processes. But for a globular cluster, typically the evaporation time scale is going to be around 10 to the 11 years, so much longer than a Hubble time. Now, one thing to kind of keep in mind is that if you look at open clusters, the crossing times are going to be fairly similar, but the relaxation times are going to be a lot shorter. And so for open clusters, you can actually evaporate them on a Hubble time. And this is part of why we only see, when we look at open clusters, if they're old, we only see really massive ones. There are also tidal effects that can accelerate the evaporation of open clusters. But this alone would give us a rough idea of why we only see massive old clusters, but we do see lower mass young clusters. Okay. So next, there's a process called mass segregation that can be important when we have relaxation timescales that are short. So what happens is the kinetic energies of the stars, not the velocities of the stars, approach the thermal distribution. So what that means is we have something that's more massive, it'll end up with a lower velocity in order to have the same kinetic energy. And that'll leave it lower in the gravitational potential well, sitting towards the bottom. Right, so the heaviest stars will sink to the center. And the plot here is from a paper by Ivan King. So the top curve is showing basically what we have is number of stars per surface area versus mass in units of solar masses. And the top curve is showing what this function looks like 7 arc seconds from the center of a core collapse globular cluster. And the bottom curve is showing something at 4.6 arc minutes. So we can actually see that the mass function of the stars is different in the two different locations of the cluster. So this mass segregation process really actually works. Okay. Now for black holes, we get some severe mass segregation effects. So we have old star clusters now, globular clusters. So the most massive stars that we have in a globular cluster are going to be the stellar remnants. Right? So the main sequence in red giant stars are around 0.7 solar masses. And then we have white dwarfs, which can go up to 1.4 solar masses, but are typically around 0.7 also. And then we have some neutron stars that are probably around 1.4 solar masses, and some black holes that are maybe 8 to 10 solar masses. So the black holes are at least 5 times or so heavier than anything else that we have in an old star cluster. And Lyman Spitzer wrote a paper in 1969 where he showed that if you have a large enough ratio between the masses of a heavy component of stars and a light component of stars, and enough total mass in that heavy component will essentially dynamically decouple from the light component. So it'll form its own little subcluster in the middle of the star cluster, and it essentially becomes fully segregated. So now we have a subcluster that has only a few hundred stars in it, the few hundred black holes. And now if we go back to our key timescales from above, the radius that we'll have will be a little bit smaller, actually, because this will be sitting right in the center of the cluster. And the relaxation timescale will be a lot smaller, because now we have 200 objects instead of 1 million or 10 million objects. And the evaporation timescale of that subcluster will be really fast. Right? So you should expect this to lead to ejection of the black holes on a timescale of tens to 100 million years. Right? So now I'll come back in a minute to why this actually doesn't go to completion. Okay. So now let's talk about how we go about detecting black holes and neutron stars in binary systems. So one thing I want to mention is that the first really convincing evidence for a stellar mass black hole was actually produced here by Jorge back in the early 90s, was it, or the late 80s? Yeah. Yeah. So there have been some reasonably strong evidence before Jorge's paper, but that was the one that really clinched that we definitely have black holes in the universe. Okay, so what I have on the left is an image of an X-ray binary system. So this is made by Rob Hines' BinSim tool. So it's a great little computer program if you want to make visualizations of what close binary systems look like. You put in a bunch of numbers for the parameters of the system, and it produces a nice computer-generated artist impression, if that's a real thing. So we have is close binary systems where we transfer mass from one object, which is a normal star, to another object, which is a black hole or a neutron star. And then because the gravitational potential well of a black hole or a neutron star is so deep, as the gas falls in, it can heat up until it gives off X-rays. And these X-rays then stand out against everything else in the sky. So there are really only a handful of objects in the sky that are as bright as the reasonably bright X-ray binaries. You know, there's the Crab pulsar and 1 or 2 AGN that just sort of get up to the bottom of the X-ray binary flux distribution. So you can go and follow up those objects individually, and then what you can do is you can make a rotation curve of the object. And then if you're able to make a rotation curve that shows that the mass function of the object, so the minimum mass that the optically dark object can have, is more than 3 or 4 solar masses, depending on what you believe about neutron star equations of state, then you know you have a black hole. And then if you can figure out a way to get the inclination angle measured, then you can make a precise measurement of the mass of the unseen object. So I also want to mention something called the Eddington limit. So this is kind of a characteristics scale for accretion. So the Eddington limit is the balance, is the luminosity at which you have a balance between radiation pressure force and gravitational force. So the radiation pressure is pushing outwards, gravity is pulling inwards. So for accretion disks, the gas is almost always fully ionized or very nearly fully ionized. So we can use Thomson scattering as the basis for driving the Eddington limit. So if you assume something spherical and with Thomson scattering dominating the opacity, then you get a limit of 2 times 10 to the 38 ergs per second per solar mass. And this is assuming that you have a chemical composition that's roughly solar. If you make it pure hydrogen, you can push that down by a factor of about 1.5. So there are a bunch of ways that you can exceed the Eddington limit, and I think Fabian can probably tell you in great detail about those. But the Eddington limit is kind of a luminosity scale where once you get above that, you need to start rethinking how you treat accretion. So the simplest way to exceed it is that most accreting objects don't have spherical accretion flows, and so you can invoke some geometric effects to allow yourself to go above the Eddington limit. You can also use Doppler boosting in special relativity if you have something moving towards you, and for example, blazars and gamma ray bursts are good examples of those. Okay, so let's talk about how we form low mass X-ray binaries. So low mass X-ray binaries are X-ray binaries with low mass donor stars. And these are actually surprisingly difficult to form in nature. So there's a key issue, just basic application of Kepler's laws, that say you take a 15 solar mass star and a 1 solar mass star, and you have that 15 solar mass star evolve by normal stellar evolution and then have a supernova explosion and turn into a 1.4 solar mass neutron star. There's no way that that system can remain bound after the supernova explosion. If you lose more than half of the mass of the binary system, it automatically becomes unbound. Right? And now we also know from looking at radio pulsars that neutron stars seem to be born with fairly large space velocities. And those large space velocities probably come from some kick at birth to the neutron star. And that makes this problem even worse. Right? So we need to come up with ways that we can hold these binary systems together. For black holes, this is a little bit less of a problem, but it's still a problem. There's another issue, too, which is that it seems that if we look at field binary stars, O stars tend to be in binaries with other O stars, not with G and K stars. So it's hard to conceive how you end up with black holes with low mass counterparts. So the solution to all of this comes from work that was developed mostly in the early 70s by a variety of people. But the basic idea is something called common envelope evolution. That if the binary system is close enough originally, as one of the stars evolves off the main sequence, its envelope engulfs the other star. And then you have two cores of stars sitting in the same envelope, and friction will bring the cores together. That releases energy, and that can unbind a lot of the envelope. So you can start off with more massive stars and keep very massive cores as long as a lot of the nuclear burning has already taken place before the common envelope happens, and leave behind a massive core which has lost its envelope, and then also probably get rid of some of the mass of the other star. Right, so this is the basic approach that you have to take in order to have neutron star binaries form, and also to have low mass black hole X-ray binaries form. Okay. All right. Now, in star clusters, we have a bunch of other ways that we can form close binary systems. So I actually took this figure from a paper about how to form binary planets. But all of the physics that goes into this figure was first developed for understanding how X-ray binaries form in globular clusters. So there are three basic mechanisms. One is something called tidal capture. If we start with, say, a neutron star and a normal star, neutron star flies by the normal star. Normally, in simple point mass Newtonian physics, if they start out unbound, they should remain unbound. Right? But if we have tidal forces that get excited on the normal star by the neutron star as it flies by, we may be able to dissipate a little bit of that excess energy and turn two unbound stars into one bound binary. The reason that this is fairly controversial is that you need to really fine-tune this in order not to inject enough energy to unbind that normal star entirely. Another one is direct collision. I'm going to show a movie from... oh, wait, no, this is the wrong movie. That's a good movie, too, but I'm going to show this one. Okay, so this is a movie from Jamie Lombardi. Okay, and what this is a movie of a hydrodynamic simulation of a neutron star colliding with a red giant. This is an idea that was first suggested by Frank Verbund back in the late 1980s for explaining a class of objects called ultra-compact X-ray binaries, which are binary systems that have a neutron star and what's probably a helium white dwarf as the donor star. And I want you to watch the timescales on this and see what the orbital period is of the final binary that ends up getting produced in this process. So a lot of this work was motivated by the discovery of a system called 4U 1820-30, which is a binary system that has an 11-minute orbital period, which sits in the globular cluster NGC 6624. So I'm going to show the movie again. So this is the neutron star, this is the red giant, and this little dot here is the core of the red giant, which is basically a low-mass white dwarf. And kind of keep looking back and forth to the time scale on this. Right, the other thing that you can notice now is that now a lot of the gas is already around the neutron star, because you can see the white dwarf, which is the lighter object, is the one that's orbiting around the heavier object. Right, so you know, how realistic these hydrodynamic simulations are is a question, but we do see these systems with orbital periods much less than half an hour, and they're very difficult to explain through any other mechanism besides something like this, or maybe something like this happening because of a triple system interaction. Okay. And then the final mechanism is something called exchange interactions. So exchange interactions, you start out with, say, a wide binary that has a neutron star and a normal star. A third star flies in. You get a temporary triple system, but triple systems, unless they're well set up, hierarchical triples tend to be unstable, and so one of the stars will end up getting ejected. And based on energy arguments, the most likely thing that happens is the two heaviest objects end up in the binary that remains stably, and it tends to be a closer binary than what you started with. So this is a good way to approach having close binaries involving neutron stars. It's also a good way to get rid of companions that are have evolved to the point where they're no longer supplying much mass. Okay. All right, so now globular cluster X-ray sources. Okay, so the Milky Way has 16 known bright globular cluster X-ray sources, and by bright, I mean basically bright enough that you could detect similar sources in other galaxies with Chandra, or that all sky instruments can detect them in the Milky Way. So these are X-ray binaries that are in outburst. Okay, and these are in 13 of the clusters. None of these is thought to be a black hole, and this is mostly because of the type 1 X-ray burst stuff I talked about before, that all of them but one show these nuclear fusion bursts, and the one that doesn't is an edge-on system where you'd expect scattering to smear out the time signature of the bursts. So it probably does have the bursts, and we just don't see them. And there are other reasons to think that that particular system is a neutron star anyway. There are also a lot of faint sources in the clusters. So this image here is from Craig Heinke's work, which is an image of 47 Tucanae. So all of these X-ray sources in this cluster would be considered faint by the definition I'm using. So there are a lot of cataclysmic variables in there. There are a handful of neutron star systems that are not currently actively accreting very much material. And there are even some coronally active binaries that we can detect in 47 Tucanae. All right, so the idea is the dense stellar environment leads to creation of tight binaries for the reasons I talked about while I was showing you the previous slide. Okay. But I'm mostly going to talk about extragalactic studies here. So the Milky Way just doesn't have enough objects. The Milky Way's globular cluster system has about 150 known clusters, and our best guess, which you can sort of see from looking at this void back here, is that there are maybe another 50 or 70 clusters which are sitting in the plane of the galaxy on the far side of the galaxy, so we haven't detected them yet. So we have a fairly small sample of objects to work with. It also turns out the Milky Way's globular cluster system doesn't span the parameter space of globular clusters very well. There's a small number of metal-rich clusters in the Milky Way. If we look at some other nearby galaxies, we see a much bigger fraction of the clusters that have metallices of around 1/3 of solar to solar. So we may need other galaxies to find rare objects like black holes, although, as I'll mention towards the end of the talk, that's probably not going to be the case. But we also need them to understand what types of clusters lead to the production of X-ray binaries, because the Milky Way, any result we get will suffer from small number statistics. Okay, so elliptical galaxies turn out to be the best place to do this kind of work, but I'll also briefly mention some work Mark Peacock did with M31. So this is an image of NGC 4472, which is the most luminous galaxy in the Virgo cluster. M87 is the most massive galaxy in the Virgo cluster, but NGC 4472 is a little bit more luminous. It has a very smooth light profile, as you can see from this image. And if you look towards the outskirts of the image, this is a Sloan image, but if you look out here, for example, you can see some of the globular clusters in the parts of the galaxy where the stellar light isn't as bright. So the other nice thing about elliptical galaxies is they tend to have large numbers of clusters. So they tend to be a little bit more luminous than spiral galaxies and to have more globular clusters per unit stellar mass than spiral galaxies do. So NGC 4472 has a few thousand globular clusters. And the other nice thing about going to the extragalactic case is that if one galaxy gives us a statistically marginal result, we can go check a few more galaxies. So within the Virgo cluster, there are probably around 100,000 globular clusters. So we can really build out much better statistical studies than we can in the Milky Way. The big advantage of the Milky Way is understanding the fainter populations like the cataclysmic variables. So here's an X-ray image of the same galaxy. This is made with the Chandra X-ray Observatory. And nearly every point source you see in this image is an X-ray binary in this galaxy, NGC 4472. We detected about 140 point sources in this image. I guess she's sort of my former student now, Tana Joseph, who just recently successfully defended her PhD thesis. She's worked with a deeper image and has gotten about 400 X-ray sources in this galaxy. Now, out of the original 140 or so, based on extragalactic surveys, we expected maybe 10 or 15 to be background AGN and maybe a few to be foreground stars, but all the rest to be X-ray binaries in NGC 4472. So in this Chandra exposure, which took about 12 hours to generate, we detected about the same number of bright low-mass X-ray binaries as have been detected since the start of X-ray astronomy in the Milky Way galaxy. Right, so if we want to do population studies of bright sources, the extragalactic systems are really the way to go. Now, of course, you won't know anything about what the companion stars are here, so that's the downside of this. This is why we need to kind of keep both sides of this going. Okay. So which clusters have X-ray sources? So these are some results from an ensemble study of a large number of galaxies. So what we have here is on the x-axis we have the colors of the clusters, which map reasonably well to the metallicities of the clusters. So we have a best guess at what the metallicity is based on the color on the top here. The colors are what are actual real physical values. So the redder, more metal-rich clusters are on the right, and the bluer, more metal-poor ones are on the left. And then on the y-axis, we have the magnitudes of the clusters. And so you can see in every example, so the blue open circles are the clusters as a whole, and the red filled circles are the clusters with X-ray sources. So you can see in every galaxy we have here, the red filled circles are skewed towards the upper right of the diagram. Right? So preferentially, the metal-rich and massive clusters have X-ray sources. So one interesting little tidbit for galaxy evolution studies to think about here is that the reddest clusters are very likely to have X-ray sources. And this is most well illustrated in NGC 1399 here. Right. This may have some important implications for understanding exactly what's going on with the cluster metallicity to color relations. Right, so if you take simple relations between color and metallicity of simple stellar populations, you'd expect that the most red clusters in NGC 1399 are actually supersolar in metallicity. People always had some caution, took this with a grain of salt because it's hard to produce supersolar gas at early times in galaxy evolution. And also there are various sources of scatter that you would have to worry about, measurement error and model error in going directly from the colors to the metallicities. But what we're seeing here is that there's an effect here that has absolutely nothing to do with any of the optical properties of the cluster in terms of what we're measuring, whether it has an X-ray source, that correlates very well with the color. And that's suggesting that we really do have some physical effect that's pushing these clusters out to very red colors here. And we only see this in NGC 1399, which is the central galaxy in the Fornax cluster. There are two possible reasons for this. One is that it's a very deep gravitational potential well that we're sitting in the middle of, so maybe metals are retained better from supernova explosions. The other possibility is that this is the only galaxy where we had B and I as our filters that we used instead of V and I. So we also have a bigger lever arm for measuring the colors, and so we may be less susceptible to having measurement errors affect things here. Okay. There's also some interesting supernova physics we can derive from what's going on here. So the number of X-ray binaries is proportional to the rate at which stellar collisions happen, and this is something that Mark Peacock found in M31, and also been found in Centaurus A by Andres Jordan. And it's also directly proportional to the stellar mass, and this is something that Michiel Smits did as his master's thesis with me in Amsterdam. So under normal supernova physics theory, we would expect that there's this Maxwellian distribution of velocities that the neutron stars are born with that peaks around a few hundred kilometers per second. And then we would expect that we would only retain the neutron stars at the low velocity end of that distribution, so out in the tail of the distribution. So we would expect that the number of neutron stars retained would be a very strong function of the mass of the cluster, because the escape velocities of globular clusters are typically 50 kilometers per second or less. Right? So if almost all of the systems are much faster than the escape velocity and we're only retaining a tail, the number that we retain is sitting out in the tail of a roughly exponential distribution. So we'd expect a really strong mass dependence. We don't see that. We see no evidence for a mass dependence here. So what that suggests is that there's a second population of neutron stars that dominate the ones that are retained, that form with very low Keck velocities. And so these are probably electron capture supernovae. So supernovae that form without an iron core ever developing. So this can happen for stars that are have initial masses of around 8 to 10 solar masses, and it might also happen if you take an oxygen, neon, magnesium white dwarf and have it accrete until it collapses. So this has also been suggested based on other grounds by Eric Fahl several years earlier, and we find an independent line of evidence for this. Okay. So I want to show a little bit of Mark Peacock's results from M31. So I think the best place to look at what the real stellar interaction rates are is M31. So what Mark did was he fit model profiles to the light profiles for star clusters in M31. And he was able to derive the core radii and the central densities of clusters in M31 using a ground-based survey from UKERT. So this was a little bit dangerous, but we actually got lucky that the UKERT people made a mistake early on and gave us a way to check our results. So we had one of the very first service run observations on UKERT, and UKERT's focal plane has a paw print, they call it, so has detectors in 4 corners of a plane, and then they move things around to fill in a square, and that allows you to image a large field of view without having chip gaps. They left out a cosine delta term when they were setting up how to move the thing around. And so what they ended up doing was giving us this big blank strip in between some regions that had been double covered. And so we pointed this out to them, and they said, okay, yeah, we'll fill that in for you. And so as a result, Mark had the nice property that he had essentially all of his clusters were imaged more than once. And so he was able to make sure that he was measuring the same parameter values under different seeing conditions, so that because the core radii of M31 globular clusters are roughly the same as the seeing that you can get in the K-band from UKERT. So it's a tricky decomposition problem. But if you measure it with 2 different point spread functions and you get exactly the same result, then you're confident that you've done it correctly. So we actually had a little bit of a fortunate accident there. So what we have here is the K magnitude on the x-axis versus the rate at which collisions are taking place between stars on the y-axis. And the diamonds represent all of the clusters that have X-ray sources, and the crosses represent the clusters that don't. So we can see is that all of the diamond sources, except for one, are above the line that fits through the middle of the cluster distribution as a whole. So what we have here is really, I think, the most convincing proof that it's really the collision rate in the clusters and not just the total mass of the clusters that's telling us how many X-ray sources we should produce. Okay, so there's something else that we were able to do with M31 data. So it turned out that there had been a Sloan survey of M31 that had just been sitting around and nobody had done anything with it. So Mark used that to get a homogeneous measurement of the clusters' colors in M31. So I think this is actually probably the best benchmark we have for testing simple stellar population models, especially for metal-rich systems. Right, so like in the Milky Way, you might think the Milky Way clusters would actually be a better place to do this. It turns out that they're not, because the Milky Way's metal-rich clusters are almost all sitting right in the plane of the Milky Way galaxy. So you have to deal both with a lot of background and foreground light from other stars and with a lot of reddening in M31 because you're not looking through the plane of the galaxy. You have cleaner measurements. Also, it's generally easier to get good photometry for objects that are 4 arc seconds in size than objects that are 10 arc minutes in size. So I think this is actually the best benchmark we have for testing stellar population models. And so what Mark did was he looked and he tested a bunch of different stellar population models for against M31, and essentially they all gave more or less the same results, except they all had this offset in the G minus R color. So it turned out that the next, roughly the day after Mark sent me this plot, and we were confused about it, Claudia Marrowstone happened to be visiting us in Southampton, and I asked her if she had any thoughts about this. And she said she knew about this problem and she had a solution for it, which was related to the way in which the stellar atmosphere models were applied to the stellar physics models. And when we took her new data, they went right through her new models, they went right through the data. And this has some implications for understanding the star formation histories of distant massive galaxies. So I do want to mention that I know there are some people here who had a different interpretation of the same data and suggested that the clusters in M31 that had some offset problems might actually be younger than 12 gigayears. Instead, it might be 8 gigayears. So if anybody in the audience is one of those people who I'd like to actually chat with you a little bit and see if we can figure out what's going on here and figure out some ways to break the degeneracies. But previously, it had been suggested that some luminous red galaxies that had the same problem might have extra star formation happening at late times, so that the color offset was fixed by adding a second component. And if we make the correction that Claudia Marstone suggested to us, then we're able to fix this problem without needing an extra second population, which is comforting in nearby globular clusters. Okay. So now I want to get back to NGC 4472. So one of the things that we found here is that we have this excess of X-ray sources in the metal-rich star clusters compared to the metal-poor star clusters. But in general, most of the data that we've been working with were one Chandra observation of the center of a field of view of a galaxy, and one HST observation sitting at the center of the field of view. So we were actually looking in the central few arc minutes, not at the whole galaxies. And a consequence of that is that we were oversampling the metal-rich clusters compared to the metal-poor clusters, because the metal-poor clusters tend to be much more spatially extended than metal-rich clusters are in typical elliptical galaxies. So we wanted to get some images that would allow us to detect more of the metal-poor clusters in X-rays or establish non-detections. So what we did was we took an image with the XMM Newton Observatory, which has a much larger field of view than Chandra. And then one of my colleagues, Kathy Rohde at Indiana University, already had a ground-based mosaic of NGC 4472 that covered essentially the whole XMM field. Okay. So we never really worked on the problem that we proposed the observations for, because we get distracted by what I'm going to finish up by telling you about, which turned out to be a little bit more interesting than that. So we have here is this circle, this green circle surrounding this object here, sitting way out on the outskirts of the galaxy. And then we have this green circle showing the optical image where we have a point source sitting there. It turns out that this object here is extremely bright for an X-ray binary. It has a luminosity of about 5 times 10 to the 39 ergs per second. So this is above the Eddington luminosity even for a typical stellar mass black hole. And this object here is a globular cluster, at least according to the colors from Kathy's data. Now, when you get out to the outskirts of the galaxy, you do have to worry more about background AGN popping up. But it turned out we also had spectroscopic confirmation that this object was at the redshift of NGC 4472. So we knew it wasn't a background object. Okay, so now this is the time series data from that object. All right, so I should actually preface this by saying that, okay, so I told you about the theoretical reasons why people didn't expect there to be black holes in globular clusters. And people had found objects that were well above the Eddington luminosity for a neutron star in extragalactic globular clusters, going back to the earliest Chandra observations of elliptical galaxies. But the problem they always had was that we look at M15 in our own galaxy, we have 2 bright X-ray sources. And so we didn't really know if what we were seeing were cases where we had a superposition of bright neutron star sources or a single bright black hole source. So when we took the light curve of this object, we could see it was varying by a factor of 6 in count rate over the course of a few hours. And this is something that you can't do with a superposition of neutron star sources. You can get a variation of a factor of 2 with a superposition of neutron stars, but not a factor of 6. Right, so we know that one of these objects was really dominating the luminosity of this cluster, and therefore that it had to be a black hole or a really perverse neutron star system. Okay. So the variability of this object shows that this is clearly a single object, and at this luminosity, I think it really has to be a black hole. The X-ray spectrum for this object is dominated by a black body component with a temperature of about 2 million degrees. So this looks an awful lot like the ultraluminous X-ray sources that Fabian studies, except that it happens to be sitting in a globular cluster in an elliptical galaxy instead of in a star-forming region in the spiral or dwarf irregular galaxy. So initially, it wasn't really clear what the black hole mass was for the same reasons that it wasn't initially clear in ultraluminous sources. The luminosity and temperature, that combination can give you a characteristic radius. And if you assume that that characteristic radius is the innermost stable circular orbit around the black hole, then it tells you that this is probably about 200 solar masses. But we actually know from a lot of the work on the ultraluminous X-ray sources that that's a very dangerous assumption. So one of the basic ideas is that once you go up to really high accretion rates, close to or above Eddington, radiation pressure should start to puff up the accretion disk, and that should probably move your characteristic radius out to a much larger spatial scale than what you get from assuming it's the innermost stable circular orbit. The other thing is that when we looked at the variability of this source in detail, all of the variability was below about 0.7 keV. And what that suggests is that what we're seeing is extra absorption from foreground gas. And if it's happening this quickly, the most likely explanation for it is that we have a disk wind being blown off by this super Eddington accretor, and that's pushing extra ionized gas out into our line of sight, and that gas is absorbing some of the soft X-rays. But at hard X-rays, that gas is transparent. Okay. Next thing that happened was we had an optical spectrum from the Very Large Telescope that we had originally used to confirm that this object was at the redshift of NGC 4472. And originally, it had just been run through some automated processing to measure the wavelengths of certain absorption lines, and they were found to be where they should be. But then we actually took a look at the spectrum, and we saw that stonking bright emission line sitting right in the middle of this bandpass. And I originally got really nervous, because I did a calculation. I found there was like a 10 to the minus 3 chance that you would have an AGN that happened to be superimposed on top of a globular cluster somewhere in this galaxy. And if I see an emission line here, maybe this is the one. Fortunately, what we did was we corrected the wavelength of this emission line for the redshift of the cluster. And when we did that, we found that the wavelength of this emission line was 5,007 angstroms. And of course, that's a well-known forbidden line of oxygen-3. And if you look closely, you can actually see a little further out. You can see the second component of this line. So then we were thinking, okay, what is this emission line? Is this a planetary nebula that's in the same cluster? Well, it turns out that the width of this line is about 200 kilometers per second. And that's too broad for being a planetary nebula. Actually, Phil Charles had been visiting Southampton from South Africa when I first started looking at the spectrum. And his response to this when he saw how broad the line was cranky, because he's been in the southern hemisphere too long. So then Dan Stern knew about this result, and he had a little bit of spare Keck time, and he asked us if we wanted to share some, and we said, of course, and we got this spectrum out. Okay? So now what we can see is that the line we were talking about in the previous paper that was 200 kilometers per second broad is actually a narrow core of this much broader line here. And so the line width now is about 3,000 kilometers per second if we go out to the broad wings. So that's really very well consistent with the idea that what we have is a strong disk wind from a super Eddington accretor, which is then being photoionized by the X-ray source inside of it. The other thing that's very interesting about this spectrum is you look at the strength of O3 here, and now look at the strength of H alpha here. Right? H alpha is actually in absorption there. Right? So we just have the no contribution that we can measure of an emission line at H alpha. So we either have a really funny ionization parameter, or we have a very strong ratio of oxygen to hydrogen. Okay, so the much more likely interpretation is that what we actually have is a lot more oxygen than hydrogen here. And the way to reconcile all of this is to say that the donor star here is a carbon-oxygen white dwarf. So what we have is a carbon-oxygen white dwarf and a black hole in a close binary system with an orbital period of maybe 5 minutes. Okay, I'm going to skip through a few of the other possibilities that we've ruled out. Okay, so now I want to mention one little thing about some impacts for braneworld cosmology that come out of this. So now what we have is a black hole that we know was formed at the roughly 10 gigayear age of the cluster. We think has a mass of around 10 solar masses. And so there's a paper by Emperon and collaborators from 2003 where they suggested that in some of these braneworld cosmology models where you invoke extra dimensions of space to explain why gravity is so weak, Hawking radiation is much faster than it is in standard four-dimensional general relativity. And what that means then is that a stellar mass black hole that's around 10 gigayears old should have evaporated by now if those extra dimensions were as big as about 3 microns. And that's about an order of magnitude better than the best constraints we have on extra dimensions from torsion pendula. So I should mention that there are some other more out there alternative theories of gravity where this doesn't happen, but at least for the most prominent one, which is the Randall-Sundrum 2 theory, we get a better constraint than what we can hope to do from laboratory physics for quite a while. I'm going to skip that too, actually. Now I want to talk a little bit about some evidence that we might have some black holes in Milky Way clusters now. One thing that we... am I going too far to the right? One issue that we've always had with these faint sources in the Milky Way's globular clusters is that we've assumed that a lot of them are cataclysmic variable stars based on relatively little evidence, just the X-ray and optical luminosities. Now, it turns out that distinguishing a cataclysmic variable star that's a dwarf nova in quiescence from a black hole X-ray binary that's in quiescence is extremely difficult to do. The optical, even if you get really good optical spectra, the differences that you'll see are very subtle. And in general, getting good optical spectra of faint sources in globular clusters is impossible. One key piece of evidence that we can look for, though, is radio emission. So on the right, we have a well-known correlation from Gallo, Fender, and Pooley of radio luminosity on the y-axis versus X-ray luminosity on the x-axis. And we can make some predictions from this correlation about how bright the radio luminosity should be for an X-ray binary that's in quiescence in a globular cluster. And it turns out that the typical numbers for nearby globular clusters are around 30 to 50 microjanskis, and we should also expect the sources to be flat spectrum. So until the EVLA was built, the amount of VLA time that you would have needed to prove that you had a flat spectrum source down at that flux level was prohibitive. So nobody had done this experiment. It turns out that we actually did this as a byproduct of a different project that we were working on to look for intermediate max black holes. So we got our first radio data set on M22, which is a fairly nearby globular cluster. And we discovered two flat spectrum radio sources. This is the central position of the cluster. This is 20 arc seconds here. So we discovered two flat spectrum radio sources sitting well within the cluster core. We looked at the optical counterparts. There were no galaxies there. There was nothing with quasar-like colors. There were some faint optical stars, which may or may not be chance superpositions. We went through all the other possibilities for what these could be, and we found that they were very unlikely to be anything other than black hole X-ray binaries in quiescence. We have an even better example from a paper that just came out on AstroPH earlier this week that Laura Chomiev put together. And so this is, again, a radio image of a different cluster, M62, and then an X-ray image of the same cluster. And this yellow source here in the radio image is, again, a flat spectrum radio source. This red object here is a millisecond pulsar that we managed to detect as well. And then we do have an X-ray counterpart for this object. And it turns out that if we look at this object, its radio, X-ray, and optical counterparts all make it look like a kind of a twin of V44 Cygni, which is actually the black hole that Jorge measured almost 20 years ago now. Yeah, so this one really looks an awful lot like basically exactly what we would have expected to see if we have a quiescent black hole X-ray binary sitting in a Milky Way globular cluster. And in this case, the optical counterpart is bright enough that with HST, at least, we might be able to do spectroscopy and measure a radial velocity curve. It also turns out the optical counterpart is variable, which is another thing that we, on fairly short time scales, like days, which is something that we might expect for a black hole X-ray binary in quiescence, but not for a background AGN. So we're really starting to see some evidence building up that we have stellar mass black holes in globular clusters in our own Milky Way galaxy now. So I think I'm just, since I'm a little bit over time, I'm going to leave the conclusions on the screen and maybe go to the question period. Okay. All right, so thank you.
Thank you, Tom, for this very interesting talk. So we have time for a few questions.
Yeah, regarding the bimodality that is found, for example, in 4472.
Yeah.
It's this has been shown on the basis of also of spectroscopic observations, not only just colors.
Yeah,
okay.
Yeah, that's right. Yeah.
Just a comment on the issue of the metallicity.
Yeah. So sorry. I think I didn't say exactly what I meant to say. So I think the issue is that the spread within each mode, people have been uncertain exactly how much of that spread was due to real spread and metallicity within a mode and how much was due to photometric conversions between color and metallicity. And I don't know that there are really enough spectra with high enough precision that you could say that. Is it?
Well, this galaxy in particular has been studied, and other galaxies, I think 39.
Yeah. Okay.
And it has been shown with I don't know how many spectra, but a quite significant
around
number.
100 typically, yeah.
Yeah, something like that.
Yeah, a lot of these spectra were taken to try to measure dark matter profiles and stuff, right?
As well.
And then you can use them for other things too. Yeah.
There is also, regarding now the cluster, I mean, there is it has been found in general in stellar clusters that there is, and in fact has been recently proposed that the star formation efficiency is the one driving the upper mass cutoff of the stellar mass distribution, and also even the IMF, the slope of the IMF. So is any relation that you might expect with the stellar mass and your findings?
I think that's a really hard problem to get at. Just because, I mean, for one thing, the present-day mass function and the initial mass function in globular clusters aren't going to be the same.
But you should have massive objects. If then it means that the upper mass cutoff should be higher than.
You're saying that because globular clusters are very efficient at forming stars, the upper mass cutoff should be higher than it would be in general populations. Okay, so that's an interesting point. So that might allow you to have, 80 solar mass black holes forming once in a while. I guess a lot of that depends too on what the stellar winds do. Yeah, I don't have a quick answer, but that's an maybe we can chat about that during the coffee, because I think that's something that I want to think more about, but that probably would take too long during the question period.
Any other question?
It's about this estimate of the evaporation time scale due to Hawking radiations. How does it depend on the accretion rate? Because I can imagine that if you feed the black hole on a regular basis for the whole lifetime of the universe, and this is very uncertain, right?
Right, yeah. So Oleg Naden worked this out carefully in the paper we published. And so basically it is if the black hole has been growing by accretion and it started out at a lower mass, and it's, I don't remember all the arguments now in detail, but he went through that carefully and showed that if you've grown enough by accretion to counteract this effect, then you started out so much smaller that the evaporation would have been even faster. So it actually, you're right that that's something that's worth worrying about, but it turns out that shouldn't actually be the solution to how you keep the black hole there.
Okay, thank you.
And if you read the Naden paper, that explains it in detail, but I don't think I can reproduce that now.
More questions?
Yes, a short question. May I ask the detection of these X-ray sources that in some ellipticals you have been looking at, and the plots you have shown us with the points that correspond to X-ray sources in general higher metallicity, especially where tend to be located towards the center of the galaxy, or is spread?
In the first paper we put out, Arno Kundu did use this statistical technique. He used a statistical technique that separated out the importance of different parameters. And it's true that the metal-rich clusters tend to be centrally concentrated, but the metal richness was a much more important parameter than the central concentration, to the extent that if you accounted for the metallicity first, then there wasn't any additional distinguishing power left from the location within the galaxy.
But the X-ray sources, in general, you say that were associated with high metallicity, so tend to be in a particular area, or are spread?
Oh, sorry, they're associated with high metallicity clusters.
Yes.
Right, and those clusters are centrally concentrated, but it doesn't appear that there's any real evidence that a metal-rich cluster that's sitting in the center of the galaxy is any more likely to have an X-ray source than the same cluster sitting further away. Mm-hmm. Did that answer your question?
Yeah, okay.
One question? No? Well, we can continue in the coffee with the discussion. So let's thank Tom again.